Today, I'm going to be presenting the Reconstructing Humans with a Biomechanically Accurate Skeleton. First of all, let's start with the task at hand that we are tackling. And this is the 3D human reconstruction. Essentially, we want to retrieve human body positions from images or videos. Here I show an image of the first model that was used, which was to invert the joints and construct this stickman model. But very early it was published this paper, Keep It Simple, which introduced a new body model which was more realistic, that uses two main parameters, the shape and the pose parameters, to construct this human body mesh. The shape parameters define the appearance of this model. Instead, the pose parameters represent the joints that are inferred from the image or the video. This model has its own problems, one of which is it is not biomechanically accurate, as in the joints modeled with ball socket joints that have 3 degrees of freedom. These introduces some problems, which are one, that the bones can appear stretched, and two, that the joint rotations, the real joint rotations of a human can be violated. And this results in sometimes poses that are not physically possible. So to address this problem, another paper was published, From Skin to Skeleton, and in this paper the authors introduced a new model which they called Skeletal, and this model aims to take same parameters, same-ish, since there are some modifications that I'm gonna describe later on the pose parameters, and uses the same shape parameters. But this model is actually a function that, given these parameters, gives back a skeleton which is biomechanically accurate. It follows a skeletal model that they introduced in this same paper, and a skin mesh that is consistent with the skeleton. In this paper, it is important to note that they also trained a regressor that is able to infer the parameters of the scale model from the SMPL mesh, not the images. This directly brings us to the paper I'm discussing today, which is Reconstructing Humans with a Biomechanically Accurate Skeleton, which aims to bridge this gap. Essentially, it trains a neural network to infer directly the scale parameters from images and videos. But how it does that? Here we can see the architecture of this model, and it can kinda be divided in two main components. The first is a neural network, in particular a VAT, which is trained to infer the parameters of the scale model. And the second component is the scale model itself, which gives back the skin and skeleton mesh. Let's delve deeper into this architecture. First of all, let us talk about the scale parameters that this VAT has to infer. And these parameters are, as I said, the pose and the shape parameters. The pose parameters are 46 parameters, not the 72 in the original SMPL paper. This is because the constraint that are posed on the joints reduces these parameters from 72 to 46. Also, the scale model takes these joints' rotation as Euler angles, but the Euler angles as a regression target doesn't give the best result. So in this paper, they chose to first infer continuous representation of the rotation, then to convert it into rotation matrices to apply the loss, and finally to convert it into the Euler angles that are needed for the scale model. The second part is the scale function, and this model, as I said, takes the shape parameters and the pose parameters and gives back the body surface vertices, the skeletal mesh vertices, and the anatomical joints locations. This is important because we need to talk about the losses of this model. And in the HSMR model, 4 losses are applied. And these losses are the losses on the scale parameters, evident distance between the matrices representations and the ground truth, and the Euclidean distance between the shape parameters and the ground truth, and the key point losses that instead penalizes the joints that are inferred. For the 2D key points, a function, which is the camera projection, is used to go from 3D joints to 2D joints. But when constructing this architecture, the authors had one big problem. This problem is that there wasn't any ground truth for the scale parameters. So the author chose to tackle this problem with a pseudo label refinement process. The idea is to start from the SMRP meshes, from them regress the scale parameters, and then during training use the 2D key points ground truth to iteratively refine these estimated pseudo ground truth for scale parameters. In practice, periodically during training, the parameters obtained initially by converting SMPL into scale and then from the VIET are taken as initial values for an iterative optimization of the objective function shown to obtain refined pseudo ground truths. Looking at the objective function, the first element is a reprojection objective that aims to align the projection of the 3D joints with the 2D key points. The second and third element are respectively pose and shape regularizers based on some sensible priors. The prior for the shape is taken directly from the original SMPL paper. The pose prior instead is constructed to strongly penalize rotations that violate predefined upper and lower limits for each joint. With this, our look to the architecture and learning framework is completed. Let's look at the experiments and results presented by the paper. First of all, let's introduce the training setup. The HSMR model was trained on the same dataset of one of the, at the time, SOTA models, HMR 2.0, and tested on several benchmarks that have either 3D or 2D annotations. Of these benchmarks, the most important is the Moyo dataset. This dataset is comprised of challenging yoga poses, which are best suited to see the real gain of biomechanically accurate approach. Before delving into the results though, I want to briefly go over the evaluation metric used. The first metric is a percentage of correct key points. This is a 2D pose accuracy metric that measures how many joints are within a certain distance threshold from the ground truth. Higher is better. The mean per joint position error instead is a 3D pose accuracy metric that gives the average Euclidean distance between predicted and ground truth 3D joint positions. In this case, lower is better. Also, it is to note that the measure units are millimeters. Then we have the procrasters aligned mean per joint position error. It's almost the same metric, but uses the alignment to measure pose and shape correctness independent of global position and orientation. Then we have the mean per vertex position error. This, instead of the joints, measures the error of the dense mesh reconstruction. And we also have his procrasters aligned version as well. Finally, we get to the results. First off, the authors compare HSMR to SOTA models and report that the model has comparable performances to HMR 2.0 on most datasets and significantly outperforms the other models on Moyo dataset, both for the joint recovery, as it's shown in the first table, and the mesh recovery, as shown in the second table. The authors attribute this gain in performances to biomechanically accurate constraints of the model and show that in another experiment done on the Moyo dataset. In this experiment, they specifically look at the elbow and knee joints and report how frequently each model violates these joints' rotation for 10 20 and 30 degrees thresholds. It turns out that the other models generate unnatural joint rotations quite frequently, in contrast to the HSMR model that has a frequency of joint violation that is very low, even on the most stringent threshold. At last, the authors gave a couple of ablation studies. The first one answers the question, why can't we simply regress the SMPL mesh using the HMR 2.0 and then fit the scale model parameters as described in the pseudo-label refinement process? They show that HSMR not only performs the same or better, but also note that the inference is significantly faster, taking 3 minutes less for each frame. The second ablation instead justifies the choice of regressing continuous representations of joint angles instead of Euler angles and the utility of the pseudo-ground truth refinement, showing that without either of those design choices, the final model has worse performances. To conclude, while looking at some qualitative results, let's talk about some limitations of this work. The biggest clear limitation is the absence of ground truths. The network could most probably benefit from precise labels. Second, even though this model can be used for videos, there is some inevitable jitter in the temporal reconstruction. This brings us to the end of the presentation. Here the paper reference in my presentation, and thank you for your attention if you made it this far into the video.